Hello students, let us start our today's session from haloalkanes and haloarene chapter. Last session we completed our preparation of haloalkanes. The one more preparation of haloalkane is from Hunt's-Dicker reaction, in which the silver salt of carboxylic acid is taken. When it is refluxed with bromine in carbon tetrachloride, it forms the alkyl halide carbon dioxide along with silver halide. So, silver acetate that can be written like this, where one of the halogen that is removed with the silver, so as silver bromide, and the bond that gets moving towards the oxygen, so that makes a group of carbon dioxide. The other halogen attacks the methyl group, so we will get CH3Br. The next one, properties of haloalkanes. Let us see the physical properties of haloalkanes. Actually, the alkyl halides are colorless when they are in pure state, but bromides and iodides, they can develop color when it is exposed to air. And lower members of haloalkanes are gases like ethyl chloride, ethyl bromide, methyl chloride, methyl bromide, etc. But the higher members of haloalkanes are usually existing in liquid state or in a solid state. The boiling point and the melting point of haloalkanes are higher than hydrocarbons of same molar mass. This is because in haloalkanes they do have dipole-dipole interaction and van der Waals forces. But in hydrocarbon, those strong interactions are not found. That's why these haloalkanes have higher boiling and melting point over hydrocarbons. Let us compare the boiling point of haloalkanes with the same alkyl group for same halogen and for polyhalogen, then for their isomeric alkyl halides. Let us see boiling point of alkyl halides for the same alkyl group, in which the methyl group we have taken, but the halogens are iodide, bromide, chloride, fluoride. So here the iodides have higher boiling point than bromide, which is then chloride, which is then fluoride. This is because the higher molar mass of the halogen atom. Similarly, the boiling point of polyhalogen compounds of same alkyl group also increases as they have more number of halogen atoms. So, carbon tetrachloride has higher boiling point because of its 4 halogen atom and its molar masses goes greater, which is then trichloromethane or the dichloromethane or the chloromethane. And hence, the boiling point of alkyl halides of different alkyl group. So here we can compare the boiling point of propyl chloride, which is greater than chloroethane, which is greater than chloromethane. Why do the boiling point increases? Once again, propyl whose molar mass is greater compared to ethyl or methyl. The next one, the boiling point of isomeric alkyl halides also changes. So, for linear chain they have higher boiling point, but the tertiary halides they have lower boiling point. This is the reason when they approaches the spherical shape from the linear chain to the tertiary one, the surface area decreases, the van der Waals forces decreases. This is the reason the N-butyl bromide, it has higher boiling point as it occupies a larger surface area where the van der Waals forces also greater. But in tertiary butyl bromide, it approaches the spherical shape, van der Waals forces decreases, area of contact decreases. That's why the tertiary halides they have lower boiling point compared to N-alkyl halide. Density. As the molar mass of haloalkane increases, density of their compound also increases. Usually, the bromo and iodoalkanes are always heavier than water because of their higher molar mass of bromine and iodine. Solubility. Alkyl halides are slightly soluble in water, but readily soluble in organic solvents like carbon tetrachloride, ether or benzene, chloroform, etc. Why alkyl halides slightly soluble in water? Alkyl halide they have weak dipole-dipole interaction. compared to water, where water it has a strong hydrogen bond. When they do mix together, the existing forces of interaction of dipole-dipole and hydrogen bond would disappear and new forces of interaction has to set up. But during the solubility of alkyl halide in water, the amount of energy released is insufficient to set up a new forces of interaction between the alkyl halide and water, and hence alkyl halide it shows very less solubility with water. Chemical properties of haloalkanes. Chemical properties of haloalkanes are broadly divided into substitution, elimination, reaction with metals and reduction. Let us take first of all substitution reactions. What do you mean by substitution reaction? One of the group when it is substituted by another group called substitution reactions, in which the haloalkanes where the alkyl group is substituted by some other group, that is said to be substitution reactions. And we know in alkyl halide the halogen is more electronegative, so the halogen that can withdraw the electron, the shared pair of electron between the carbon and halogen, hence it develops a partial positive charge and a partial negative charges over the carbon and halogen atoms. So the formation of the negative charge makes this halide as a nucleophile, and the developing of partial positive charge over the carbon that makes it as a electrophilic site. So now this dipole has a nucleophilic site and the electrophilic site. To this, the carbon as it is electron deficient that can seek for the nucleophile. When the incoming nucleophile is strong enough, it may able to replace the weak halide ion that is attached with the carbon, and hence we will get the substituted product of alkanes along with the leaving group. Here the leaving group is also a nucleophile. So one nucleophile, that halide ion, is being substituted by another nucleophile. Such reactions are said to be nucleophilic substitution reactions, and in which the reactions are represented as SN. S stands for substitution, N stands for nucleophile. And these nucleophilic substitution reactions are depending on the effect of alkyl group, that is the R group, and the effect of the incoming nucleophile, and the effect of the leaving group, and effect of solvent. When we say the effect of the structure of alkyl groups, they may have a primary structure, secondary structure, tertiary structure. So when number of alkyl group increases in their structure, that may influence that nucleophilic reactions also. And the effect of the nucleophile which is being used to replace the halide ion should be strong enough. Then it can replace the halide ion of alkyl halide, and hence we can proceed the reaction. Then effect of the leaving group should be large enough. That means iodide, bromide, chloride, fluoride we have, in which the iodide is considered to be a better leaving group because of its large size. So the effect of the leaving group should also influence the substitution reaction. And then effect of solvent. This solvent that plays an important role in substitution reactions. We have two types of solvent. One is said to be polar protic solvent, and the other one is polar aprotic solvent. Let us discuss more about the effect of solvent in substitution reaction. The effect of solvent over substitution reactions. We have two types of solvent, polar protic solvent and polar aprotic solvent. Protic solvent means those solvents able to provide protons, H plus ions. polar aprotic solvent. Here, these solvents do not have that proton or the H plus ions. Examples for polar protic and polar aprotic are, we can have alcohol, water, HBr. In all these cases, we may find the hydrogen is present that could be left out as H plus ion. But in the case of polar aprotic solvent, the acetone or dimethyl sulfoxide where the group doesn't have the proton. That's why these are said to be aprotic solvent. So how these proton influences the reaction? They can split up into greatly H plus and OH, and the OH minus that surrounds that alkyl group and H plus that surrounds about the halide ion. So here the halide ion is not at all free and the carbon halogen bond unable to break in presence of polar protic solvent. But in the case of polar aprotic solvent, as it has no proton, then the nucleophile will be free and can easily be broken by any other nucleophile. So carbon halogen bond can easily be broken by the incoming nucleophilic reagent. That's why the polar aprotic solvent that facilitates SN2 reaction, but the polar protic solvent that facilitates SN1 reaction. The secondary alkyl halides, they prefer both SN1 reaction as well as SN2 reaction. So in presence of polar aprotic solvent, secondary alkyl halide undergoes SN2 reaction. But in presence of polar protic solvent, the secondary alkyl halide undergoes SN1 reaction. Let us discuss about bimolecular nucleophilic substitution reaction. This reaction is represented as SN2. S stands for substitution, N for nucleophile, and the 2 it represents bimolecular. What do you mean by bimolecular? The rate of reaction that completely depends on both the concentration of nucleophile and that of substrate. Substrate is the target molecule to which the nucleophile attacks. The nucleophile is the incoming group which is able to replace the other nucleophile of halide ion. So, rate of reaction means the rate at which the reaction can carry out, that means the speed, or we can say the change in concentration of reactant with respect to time. How far the concentration of reactant gets decreased with respect to time is said to be rate of reaction. Okay, now this primary alkyl halide is taken for SN2 reaction. And this is the simplest halide, CH3X, methyl halide is taken, to which a nucleophile, it approaches the carbon just the side opposite to that of halide ion. This is why the halide ion is a nucleophile, the incoming group also nucleophile. When nucleophile approaches just towards the halide ion, because of the similar charges, they repel each other. So to avoid the repulsion, the nucleophile that attacks the carbon to the side back of halide ion attached to the carbon. Because of this backside attack, it makes a transition state in which the sp3 hybridized carbon changes into sp2, that means the CH3 only we have to consider, because the other two groups are partially bonded with carbon. The halogen is being to be removed by taking away its shared pair of electron. But the OH minus, the incoming nucleophile, it tends to make the bond with the carbon atom. So, in this transition state, the breaking and making of bond takes place, and the other 3 hydrogen atoms that goes to the plane of the paper, and The carbon halogen bond, it goes weakened because halogen, it withdraws the electron from the carbon atom. At the same time, the OH carbon bond, it becomes strengthened. This is because the oxygen, it releases electron to the carbon to make a new bond. So finally, the halogen, it takes away the shared pair of electron, thus it makes chloride ion, and the OH that seeks the carbon, so it forms alcohol. So if the nucleophile is OH minus, then we will get alcohol as the product of the reaction. In this case, due to backside attack, the molecule is totally changed its spatial arrangement with respect to the plane. See, the halogen carbon is attached to the side right of the molecule. But in the product, we may find the OH is just behind the carbon. That makes the total spatial arrangement of the compound, resulting compound, it gets inverted. This known as inversion of configuration, and it is also known as Walden inversion. This is also called Walden inversion because Walden only first of all identified the change in spatial arrangements of the groups attached to the substrate after the reaction. So this is known as Walden inversion. Reactivity of different alkyl groups towards the SN2 reaction. We have methyl, ethyl, isopropyl and tertiary butyl. When we go from methyl to tertiary butyl, we may find the number of alkyl group increases in its structure. In the first case methyl, I have only 3 simplest atom of hydrogen with the carbon. But in ethyl group, that carbon it has 1 methyl group along with the 2 hydrogen. In isopropyl, that carbon it has 2 methyl group. But in tertiary butyl, that carbon it has 3 methyl group. So the increasing number of alkyl group from methyl to tertiary butyl, it makes the molecule goes larger in size. So due to increasing size of the alkyl group, that may hinder the approach of nucleophile to attack the carbon atom. So that creates the inhibiting effect or steric effect. And hence the nucleophile can easily approach the carbon where the atoms are simplest and which do not hinder the approach. So the rate of reaction or the reactivity of alkyl group towards SN2 reaction is methyl group, it shows the much more greater reactivity towards substitution and greater which is than ethyl and isopropyl and then tertiary butyl. For the given halide, for suppose if at all the halide is iodide, the iodide reactions are much more effective than chloride or bromide. Why? Because the carbon iodide bond length is larger and the iodide can easily be removed by the incoming nucleophile. So the effect of nucleophile, that is the leaving group, if at all much larger, then that can be easily removed by the incoming nucleophile. And here the solvent, SN2 reactions are favored by aprotic solvent. That means polar aprotic solvent. Polar aprotic solvent, it does not solvate both the alkyl group and the halide ion, and hence the incoming nucleophile can easily substitute the halide ion. So the effect, the solvent to be used for SN2 reaction must be polar aprotic. And the alkyl group effect also we discussed. Nucleophile, the incoming nucleophile must be strong enough in order to replace the halide ion. So all the 4 effects, one is effect of the structure of alkyl group and the effect of leaving group and the effect of incoming nucleophile and the solvent. Based on these 4 factors only, the compound which undergoes SN2 reaction is decided. The next one is unimolecular nucleophilic substitution reaction. It is given as SN1. S for substitution, N for nucleophilic and 1 for unimolecular. What do you mean by unimolecular? Here the rate of reaction that depends on the concentration of only the substrate. It does not depend on the concentration of nucleophile. But in SN2, rate of reaction depends both on nucleophile as well as the concentrate. The nucleophile is the incoming group. But in this case, it depends, the rate of reaction totally depends on the concentration of substrate, and hence it is termed as unimolecular substitution reaction. So it follows a two-step reaction, but SN2 follows a single step reaction. The simultaneous breaking and making of carbon halide carbon nucleophile takes place. But in this case, here that it takes two-step reaction. The first step is formation of carbocation. Actually, this step is a reversible step and it is a slowest step. So this step is a slowest step. So this slowest step only determines the order of the reaction. That means whether it follows the first order, the one, or the second order. In this case, as it is slowest step, the bromide ion that leaves away with its shared pair of electron, and hence the sp3 hybridized carbon is turned into sp2 hybridized carbon of carbocation, and the carbocation is tertiary carbocation, a more stable carbocation. The second step is attack of nucleophile to the carbocation. This carbocation is free from any nucleophile, and hence the incoming nucleophile which may attack the carbon on either side of the direction, and this makes the step is the fastest step in which we are getting the two product. One in which the inversion takes place, the other one in which the retention takes place. So when the nucleophile attacks the carbocation, it may go to the side towards the halide ion where it is present, or it may go to the side opposite to the halide ion present. As a result of this, we may get the inverted product and the retention product. So if OH minus goes to behind the carbon, we will get the shape or the geometry, that is the spatial arrangement of the molecule is inverted. Suppose if OH groups just to the side towards the halogen where it retains their configuration. So as a result of attack of nucleophile, thus carbocation, it may give rise to the inverted product as well as the retention product. So here also the solvent that plays a vital role to decide the reaction. In this case, we have to take a polar protic solvent. Why do we take a polar protic solvent? So the influence of solvent is polar protic solvent, as the alkyl groups are bulky enough. The proton that cannot be solvated by such larger group, and hence the nucleophile will be free and the bulky alkyl groups will also be free from the solvation of that solvent. So polar protic solvent, if at all taken, then the rate of reaction will be faster, since the groups alkyl and the nucleophile cannot be solvated effectively, as the alkyl group is bulkier and it would not allow the solvation, and hence SN1 reactions are taking place in polar protic solvent, but SN2 reactions takes place in polar aprotic solvent. Reactivity of alkyl halides towards the SN1 reaction. In this, the tertiary carbocations are more reactive than secondary carbocation, which is then primary and then methyl carbocation. Why the order of reactivity reversed? Because in these cases carbocation is formed as intermediates. The stability of carbocation only the tertiary, which is much more stable than the methyl carbocation. So according to the stability of carbocation, that makes the reaction to facilitate faster if at all the alkyl group is tertiary. And the solvent should be taken as polar protic solvent because the alkyl group and the halide ion cannot be solvated more effectively as the alkyl groups are much bulkier. And the leaving group must be in larger size like bromide or iodide, so that can be leaving the carbon very easily. And the nucleophile incoming one should be strong enough to attack. And alkyl group must be more stable because the intermediates are carbocation. So these are the factors that influence the rate of reaction towards SN1 reaction. Let us see some of the nucleophilic substitution reactions carried out by alkyl halides. So here we have taken too many number of nucleophiles. According to the nature of the nucleophile, we will get the different products. Let us see one by one. If the reagent is aqueous sodium hydroxide or water, in case of sodium hydroxide, the nucleophile becomes OH minus. In case of water, it behaves as a neutral nucleophile and from which the OH will be added. So, when aqueous NaOH or neutral water is taken as nucleophile where the OH replaces the halide, so alcohol will be the product. Instead of alcohol or water, if we are taking the sodium salt of alcohol, it is said to be sodium alkoxide, where the alkoxy group becomes the nucleophile and hence we are getting the product of ROR. So these are ethers. If we have ammonia or primary amine or the secondary amine as the nucleophiles, these are all neutral nucleophile because they have a lone pair electron over the nitrogen atom. Just like water, in water also oxygen has lone pair electron. So these lone pair electron, they can be given to alkyl group to make their respective product. If ammonia is the nucleophile, the product will be primary amine. If primary amine is taken as the nucleophile, we are getting the secondary amine as the product. Or if the secondary amine is taken as the nucleophile, then the product will be tertiary amine. And the potassium cyanide, silver cyanide, potassium nitrite, silver nitrite, these are having ambident nucleophile. What are called ambident nucleophile? The nucleophile which has more than one nucleophilic site are called ambident nucleophile. In cyanide, in one case it behaves as the carbon carries the negative charge, but in the other case nitrogen carries the negative charge. So due to the difference in ionic character of potassium cyanide and silver cyanide, the one that makes the bond between the nucleophile and carbon, it becomes stronger. So which type of bond goes stronger, that prefers for the formation of compound. See, in the case of alcoholic potassium cyanide, the nucleophile is cyanide where carbon carries the negative charge. And this carbon, when it gives its electron to the alkyl group where carbon-carbon bond becomes much stronger rather the nitrogen to carbon. This is why the potassium cyanide is highly ionic in nature and it can able to completely dissociate into potassium ion and the cyanide ion. But in the case of silver cyanide, the silver, it is not a S block element, belongs to D block and its electropositivity is much smaller than potassium and hence the silver cyanide, it has covalent character. because of this covalent character, the nitrogen takes the negative charge than carbon. So in this case, the link of nitrogen with the carbon makes more stable and stronger than carbon to carbon, and hence silver cyanide, it gives alkyl isocyanide as the product, and the cyanide isocyanide are functional isomers. Similarly, potassium nitrite and silver nitrite, once again they are differing in their character. It is completely ionic, this is partially ionic, so the silver nitrate is associated with some covalent character. So because of potassium nitrite, where the oxygen carries the negative charge and the link of oxygen with the alkyl carbon becomes stronger, and hence alkyl nitrite is formed as a product. But in the case of silver nitrite, nitrogen carries the negative charge and hence it makes the compound of nitroalkane. Once again, nitrite and nitroalkanes are functional isomer. And besides that, we may have the silver salt. This is in which we have taken RCOO minus Ag. So silver alkanovate, in which the alkanovate group behaves as nucleophile. When it acts with the alkyl group, we will get the product of ester. Or in the case of the strongest reducing agents like hydrides, these are metallic hydrides, in which the hydride ion behaves as the nucleophile, where it links with the alkyl group to form hydrocarbon. Similarly, when we have alkyl metal, where alkyl carries the negative charge and the alkyl group behaves as the nucleophile, so we will get the higher alkane. So these are the reactions in which depends on the nucleophile we select, we get the product of their respective compound. The next chemical properties of haloalkane is elimination reaction. Elimination reaction is also called dehydrohalogenation, removal of hydrogen and halogen. And the hydrogen is being removed from beta carbon, so it is also termed as beta elimination. Just like substitution reactions, elimination reactions are also of E1 and E2 reaction. That is unimolecular elimination reaction, it is bimolecular elimination reaction. All these steps we can compare even for substitution reactions. See, here in unimolecular reaction, rate of reaction is totally depending on only the concentration of substrate, while in E2 the rate is depending on both concentration of as well as the nucleophile. And the unimolecular elimination follows two steps, in which once again the intermediate carbocation is formed, but here it follows a single step reaction. That means the simultaneous approach of nucleophile and the elimination of nucleophile that it takes place together. And the unimolecular reactions are favored by the tertiary alkyl halides, while in bimolecular it is primary alkyl halide. And the elimination reactions are decided by the nature of the solvent. So elimination in which a polar protic solvent that facilitates elimination. In the case of tertiary alkyl halide, a polar protic solvent that facilitates the elimination reaction. But in primary alkyl halide, polar aprotic solvent that facilitates the E2 reaction. Let us find the E2 reaction. E2 reaction is carried out by primary alkyl halide. Before going into the reaction, we should know what are alpha beta carbon. The halogen, the functional group that is attached to the carbon is always alpha. Whatever the functional group, whether they may carry the carbon itself in its functional group or other than the halogen containing functional group, then that attached to the carbon is said to be alpha carbon. And the successive members of carbons are beta, gamma, delta. We can proceed. So I have taken ethyl bromide, bromoethane. It is a primary alkyl halide when it is treated with alcoholic potassium hydroxide. Alcoholic potassium hydroxide, a polar protic solvent. So in this, the OH minus that abstract the proton from the beta carbon, simultaneously that can leave the halogen, and hence we are getting alkene, potassium bromide and water. So the mechanism, we can take the base nucleophile that abstract the proton from the beta carbon. Subsequently, the carbon hydrogen bond moves towards the adjacent alpha beta carbon and where the halogen takes away its electron. So in this K plus OH minus, that OH minus with the hydrogen forms water and K plus with the halogen that forms potassium bromide and alkene is the product. The reactivity of alkyl halide in E2 reaction is primary alkyl halide. So we can write CH3 CH2 X which is greater than CH3 CH3X which is greater than CH3 CH3X. So in this case we need to have at least 2 carbon in an alkene. The first member of the halide will be the compound having 2 carbon atom. So the order of reactivity of alkyl halide towards E2 reaction is the primary, which is then secondary, which is then tertiary. Once again, this is because of the steric effect or inhibiting effect of alkyl group towards the OH minus. So the ethyl group, it has only one simplest methyl group, the other 2 atoms are hydrogen. So the OH that can approach the beta carbon, but in the case of secondary or tertiary, the number of alkyl group increases and hence the approach of OH minus will be hindered. E1 reaction. So elimination reaction in which the rate of reaction depends on only the concentration of substrate, not on the nucleophile, are called E1 reactions. So in which alcoholic KOH that eliminates the halide ion as potassium bromide and water. So we will get alkene. In this case, this is the functional carbon to which halogen is present. So this is alpha carbon. Besides this alpha carbon, we have 3 more methyl group. All of them are beta carbon because all the alkyl groups are similar alkyl group and those are referred as beta, beta dash, beta 2 dash like. But all the alkyl groups are similar and hence we can remove the proton from either of the alkyl group. So in this mechanism we may find the first step is formation of carbocation. The first step that proceeds with the removal of halide ion from the carbon halogen bond and hence it forms a tertiary carbocation and the halide ion. And once again the reaction is reversible and the step is the slowest step. Once carbocation is formed, already we have the 3 methyl group which all of them have beta. So one of the hydrogen from either of the methyl group can be removed by the incoming nucleophile as water. So the OH minus that abstract the hydrogen ion from the alkyl group and subsequently the bond moves between the carbon-carbon so that it develops a double bond between the carbon atoms. So here we are getting isobutylene or 2-methyl propene is formed. Once again E1 reaction that is favored by the tertiary alkyl halide which is greater than secondary which is greater than primary. Order of reactivity of alkyl halides towards elimination reaction that can be given. Primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. When I make primary alkyl halide is greater than secondary or tertiary, that facilitates the E2 mechanism. But the reverse order is the primary less than secondary which is less than tertiary. So in this direction we can say the E1 reaction that facilitates the one. So in the opposite direction tertiary alkyl halides that undergoes elimination reaction much faster than primary. But in E2 mechanism, primary alkyl halide that undergoes elimination much faster than tertiary alkyl halide. So in this direction we are discussing about steric effect, and in this direction we are discussing about the stability of carbocation, because the carbocations are formed as an intermediate in the course of E1 reaction. The same thing that can be taken for even substitution reactions, where we have to take this is as SN2, this is as SN1. But in substitution, besides ethyl halide, we will take methyl group also. The next property of haloalkanes is reaction with metals. So, in Wood's reaction, we have studied about this reaction already in hydrocarbon, where we prepared the higher member of alkane under the topic of alkanes. So, in this, two molecules of similar alkyl halide, the alkyl group must be similar. The different alkyl group will give the cleaved product, so none of the product will be the major one, and hence in the Wood's reaction the alkyl group must be similar. They can be branched one, but both of the alkyl group should be similar. So when two similar alkyl halide is treated with the sodium metal in presence of dry ether, it gives the higher member of hydrocarbon, in which the number of carbon increases. So wherever the reaction that involves the increase of carbon atom, those reactions are said to be step-up reaction. So this is also one of the step-up reaction because we are increasing the number of carbon atom. Let us take a proper example, bromoethane or ethyl bromide. With the other molecule of bromoethane with the sodium metal, it forms the N-butane as the product. So reactant, it has only 2 carbon, but the product, it has 4 carbon atom. So these reactions are said to be step-up reaction. The next one, Grignard reagent. This reagent actually prepared by Victor Grignard by taking the magnesium metal in alkyl halide and in the condition of dry ether, where it forms a liquid of alkyl magnesium halide. This is also said to be organometallic halide, or we can say organometallic compound. This Grignard reagent is a very good synthetic reagent from which we can able to prepare all the derivatives of hydrocarbon. Even hydrocarbon can also be prepared from Grignard reagent, and the Grignard reagent is highly unstable and hence it is more reactive. Even the presence of traces of water that could make Grignard reagent into alkane or the alcohol or even the amines, if at all present with the Grignard reagent, then the Grignard reagent is correspondingly converted into their alkanes and it forms the magnesium hydroxyl substituted or amine substituted magnesium halide. Okay students, let us close our today's session. Today we have seen about the physical and chemical properties of haloalkanes and more important concept of substitution and elimination reactions we have completed. Let us see the next class with the new topics. Until then, bye bye.